Welcome to this session on heat transfer with advection as part of the NPTEL MOOC on transport phenomena in materials. This is also called as convective heat transfer. So, the outline for this session is as follows. We will take up heat transfer along with fluid flow in a rectangular coordinate system. The first two cases are in rectangular system, and we will then move on to the cylindrical case also. And in a very simple problem, while looking at the concept of Nusselt number, we will also look at a spherical coordinate system. And through these sessions, we will also be introducing new concepts like what is a bulk temperature, what is a Nusselt number, and so on. And we will end the session with empirical correlations of Nusselt number, which basically will give us the heat transfer coefficient. And once the heat transfer coefficient is available, then we can use it as a boundary condition in the problems that we normally encounter in metallurgy. Now, the domains for this session will all be liquid domains. So, which means that this fluid flow is taking place inside the domain, and we want to understand how that flow will couple with heat transfer. So, let us take a trivial situation where we can rule out the effect of flow on heat transfer. So, we are looking at heat transfer normal to the unidirectional flow. So, you could then pose the problem with the following assumptions. So, let us look at the equation which is generalized Fourier heat conduction equation in rectangular coordinate system, and say that the situation is where you have flow taking place in one direction, then the heat flow is in the other direction. Okay. So, this is a situation that we want to look at. So, if you take the state assumption, then you do not need this term, and then if you say that the temperature is varying along only x1 direction, then you would not need the terms like this. So, all these are gone because of the assumption 2. And then we say that the unidirectional flow is along the u2 direction. So, this is x2 direction, u2 is in the x2 direction, which means that u1 is not there and u3 is also not there. Now, you could see that though u2 is present, it is multiplying with this term here, which is again dropped. So, which means that the flow is not affecting the temperature gradient at all on the advective term. So, this is the reason why, for example, it is necessary to look at which way is the flow compared to the unidirectional heat transfer. However, the flow can also affect in another manner. Okay. So, it can affect through the source term that is present here. So, if you drop all the terms on the left hand side, you have got only this term and then the source term. Okay. Now, sometimes the unidirectional flow is termed as plug flow. So, which means that this u2 is a constant, and it means it is not a function of the other two variables x1 and x3, which means that there are no velocity gradients that are there. Then if you look at viscous dissipation, which is basically caused because of velocity gradients, then g will be 0. So, for a plug flow you can say that g is 0, and in such situations then you could also drop this term, which means that your generalized Fourier heat conduction equation in case of a steady state heat transfer in one direction and flow in the normal direction, then the thermal profile is actually not affected by the fluid flow. So, sometimes these are the situations where apparently the flow is there, but actually it does not affect. In situations where the plug flow is not the case, but unidirectional flow is actually the case with the variation of velocity in the other two directions, then you do have a viscous dissipation coming in. So, viscous dissipation is written in this form, and if you then recollect the Newtonian viscosity approximation where we have already seen, then this basically is tau, which is then given by mu times dou u2 by dou x1, and then this itself is again dou u2 by dou x1. So, you could then write the g as this. So, which is basically watt per meter cube, and if such a viscous dissipation is taking place, then it goes into the g term here and affecting the temperature profile. And then you could actually look at this equation and then solve it by integrating twice, and you can then look at the solution that will come in this form. And in the process of obtaining it, we have made assumptions like the boundary condition saying that the domain on both ends has temperature T0. And when is this kind of a situation possible? In situations like bearings. So, in situations where you have got, for example, outer wall moving and inner wall stationary, there is relative motion between these two, and then this thickness which is delta is very small compared to the radius. So, the radius is r. So, compared to r, if delta is very small, then we can have this situation. And what kind of a flow are we then talking about? We see that we are having a flow of this nature. So, clearly there is a gradient, and that gradient is what is causing the viscous dissipation, which is causing the heating. Now, the temperature variation is across this distance, and you can see it is parabolic. So, which naturally means that you would have the maximum heat at the center, and therefore, if this was a velocity profile, then the temperature profile would have something of that nature. Okay. Now, the maximum heat that is actually obtained here, this delta, is the reason why, for example, what is in this region is getting hot. So, which means that this usually is the lubricant. So, which means that lubricants do get hot because of viscous dissipation when delta is very small and the velocity gradients are steep. And that is one reason why, for example, lubricants have to be designed so that their viscosity does not fall significantly with increasing temperature. Now, that part apart, let us look at how this solution is going to look like. You can already see that the solution is written, and then you could then plot it. So, you could see from the profile that the temperature this way would be T naught if you look at the functional form, and there will be something maximum here, okay, and this distance is x1 direction, okay, and this parabolic form is something very common to us. We have already seen this coming many times, and you could already see that whenever you have got the Laplacian term playing a role along with a source term, then for example, you would have, so whenever you have this kind of situation, then usually this will be parabolic, okay, if this is constant. Okay. So, that is something that we already saw, and here we can already see that in the problem similar kind of a thing is coming. So, without even solving, one can already guess what is going to happen. Now, you could already see that this problem can be solved with the different boundary conditions, such as there is no heat flow across one of the walls, for example. What would then happen is the parabola will get shifted up. So, if you say that one of the walls is insulating, for example, then it would mean that you may have a temperature profile which is still parabolic, but then having its maximum on the surface, because then the slope of the temperature profile is 0, and that would accommodate. So, like this you could actually look at the solutions for various boundary conditions. So, this is one way by which the fluid flow is affecting the temperature profile. Now, let us see what happens when the fluid flow is actually not normal, but parallel to the unidirectional flow. So, here is a situation, you have the flow along the x1 direction. So, u is this way. So, heat transfer also is in the same direction. So, which means that basically anti-parallel or parallel, it is not normal definitely. So, which means that they will have some coupling that will take place. What we want to inspect is how would the temperature profile be. So, T as a function of x, and we want to see whether this is going to be a straight line or not. So, our guess would be that it may not be straight line. So, the way we solve is as follows. We again write the governing equation and see what would turn out to be. So, we see that steady state is to be assumed, and then the unidirectional velocity which is along the x1 direction. So, u2 is not there, u3 is not there, okay, and the t is varying only along the x1 direction, which means that along the x2 and x3 directions it is not there, and of course, these terms are anyway 0, and then there is no heat generation. It is an approximation. We want to say that we do not want to look at the viscous dissipation at this moment. So, which means that the governing equation will have only these two terms, which then is written here, okay, and you could then see that these and these, okay, can be written as T dot and T double dot, which is then converting the equation to be a simpler form. So, you could then write this as 1 by T dot into dou by dou x T dot, because that is nothing but this is T double dot, okay, is equal to u1 by alpha. So, when you integrate, you would get logarithm, and then it means that logarithm T dot is equal to u1 x by alpha plus constant, and then when you exponent you will get T dot is equal to exponential of u1 x by alpha into some constant. Okay. So, like that you can actually look at the solution, and then when you integrate this you get another constant, and that constant is called b here in our situation. So, you could then finally see that the solution should be exponential form. Okay, because here you are writing dou t by dou x is exponential. So, solution also will be exponential. Now, the a and b constants can be determined using the boundary conditions, which we said that at x a it is T a and x b it is T b. So, you could do that and then solve the constants, and then you will get them as a very symmetric expression with exponentials. And at this juncture, how the profile would look like is something where we can introduce a new concept called Peclet number. So, that is basically to look at this quantity that is appearing in the exponential, which does not have units. So, you can then think of a number for that, Peclet number. So, Peclet number is defined as velocity into distance over the diffusivity. Okay. Now, in the limit of a Peclet number being very small, okay, then what happens is the velocity is very small. In such situations, we already know that exponential of a small argument is approximately 1 plus that argument. Okay. So, with that approximation, what happens is that when you substitute this into here and you do the same thing for all the 4 exponentials, then you would see that the expression would come out to be very simple. It would just come to be the same differences in distances as temperatures. In other words, it is going to be just a straight line approximation, which is basically a conduction solution. So, we have retrieved the conduction solution, though convection is the starting point in the limit of convection being negligible. So, that means that the solution is valid. Now, how does this solution look like when we plot? So, for some typical values of alpha and u, you could plot, and you could also vary the u to be either positive or negative, and that we do in a simple Mathematica script here, 2-line script, and you substitute some values as you like, and then you can make a plot. So, you can say that on the left hand side is T a, on the right hand side is T b, and then the distance is here x1, and then I am plotting the temperature here. So, you could then see that you can have the flow to the leftwards and flow rightwards, and for both these situations the temperature profile is actually deviating from the straight line. The straight line is actually the conduction solution, which is actually available here, which we already know, okay, because straight line is a solution for the conduction equation when we drop all the terms except the diffusion term. Now, just look at this profile a bit carefully. Midway between the two walls A and B, x A and x B, midway you see here, if you go up, then where we cross over, that will be the temperature, average temperature between the two walls, and this is only true when there is no flow. And when there is a flow, what would happen is that the temperatures are different, okay, depending on the orientation of the flow. So, which means that basically you would not be reasonable to approximate the temperature halfway when there is a flow along the direction of the heat transfer, and you must always see that the temperatures are closer to the upwind, okay, or upstream temperature. So, you can see that upstream, this is, for example, these two are for the flow going this way. So, this is upstream and this is downstream. Okay, here these two cases are for the flow in the positive direction. So, this is upstream and this is downstream. So, which means that the temperatures are approximated to the upstream, whether it is positive or negative, and so you should always say upstream or upwind temperature is a good approximation for temperature halfway, and this is the case when the fluid flow is present. If the fluid flow is not present, you can actually take the average temperature to be the temperature halfway. So, it is very important effect of the flow on the heat transfer when the flow is along the direction of heat flow. Okay, so we have already seen these temperature profiles when we were drawing the steady state heat transfer profiles in an earlier session, and we have been always drawing, for example, the temperature distribution in a liquid domain. Okay, whenever the heat transfer is happening, in the case of hot body in contact with cold body, we are actually drawing this way, so that heat is going that way, and in the case of cold body with hot fluid across, then we will look at the heat going that way and the profile is drawn. So, you could see that in both the situations we are drawing profile in an asymptotic manner, and the slope here is what we say we are not very sure, and that is the reason why we want to write the heat flux in this direction. For example, E is given by H into delta T, because we do not know the slope. You can now see the reason for it. The slope here, for example, is a function of the velocity magnitude, which we do not know in a general situation. So, naturally we then cannot use the Fourier heat conduction equation here, we need something different. So, we use a dump factor heat transfer coefficient. So, this is the reason, and these exponential profiles are drawn earlier itself, but we now know the meaning why we are drawing that way. Okay, now we take a slightly long problem to solve, but at the end of it we have a very elegant solution that is coming up. So, this solution is basically what we are seeking for temperature profile in a cylindrical coordinate system for pipe flow. So, what we are saying is that cross section of the pipe flow is circular, and we say that the velocity profile u z as a function of r should be exactly how we have derived earlier, that is basically the so called Poiseuille flow. Okay. So, this profile is going to affect the heat transfer, and we say that the liquid that is entering is at a temperature T naught, and what is coming out at any z is T z, and T z is then a function of R. Okay. And that means the temperature is a function of R and Z, and the temperature is changing because there is heat that is coming in through the periphery. Okay. So, through the circumference we are getting the heat that is coming in, and that is given as a constant heat flux Q naught. So, remember it is a constant heat flux on the surface Q naught problem. If the problem is changed to constant surface temperature, then that becomes a separate problem. So, here we are talking about constant heat flux, and that helps us make some of the assumptions. We again make some assumptions like fully developed flow. So, which means that this is given by the Poiseuille expression, then axisymmetry, so no theta variation, okay, and constant inlet temperature. So, the T naught is constant, and we say that flow is affecting the thermal field and not the other way, which means that we decide the fluid flow and then directly use it in the temperature equation. Then how the temperature is changing will not change the flow by way of affecting the properties. So, we will not look at the cross coupling, we will look at only one way coupling. Okay. So, look at this problem and let us see how to go about. So, here is the overall map of these concepts, because it is a long derivation. I want to just keep the bird's eye view. So, we want to derive the thermal field for a pipe flow, and we will first seek the solution. So, this is slightly long. Okay. And once the solution is available, then we want to look at what with the surface temperature and what is called the bulk temperature. We will define that later on, and from these two we want to define the heat transfer coefficient, and then from there we want to then come to the concept of Nusselt number, which comes out quite an elegant expression in this problem. So, let us now embark on this particular process. So, the equation to start is basically generalized Fourier heat conduction equation for a cylindrical coordinate system, and that is what is written here. So, you would see that this has many terms, and we are going to drop many of them. So, steady state implies that we can drop this term, okay, and the unidirectional flow is along the z direction, which means that u r and u theta are not there. So, which means that you could then drop this term and this term. Okay. And there is an axisymmetry in the problem, we say then T is not varying as a function of theta. Okay. So, we will drop this term, okay, and there is no heat generation term, and which means that you could actually see that viscous dissipation is neglected. So, which means this is the fourth term. Now, we need to have a decision here, and we say that here the dou T by dou Z is not a function of z, which means that the maximum way by which temperature is varying along the length is only first order slope and not. So, we would like to drop this off. Okay. So, which means that we can actually simplify the solution a bit. So, which then leaves us with these terms, and we have the flow decided already, the functional form, which is what we would actually introduce into this. Okay. So, then the governing equation would come out to be here in this manner. So, you would see that there is a dou T by dou Z term and then dou T by dou R term. So, that we actually seek temperature as a function of R and Z. Okay. So, that is what we are wanting. And now, the boundary conditions are to be given. The boundary conditions are such that at Z is equal to 0, that is at the beginning of the domain, this is the inlet temperature. Okay. And the condition here is basically the flux through the wall, and then we also make one more assumption or limitation to the solution. We say that at the axial direction the temperature is finite, which means that in case when we are integrating, we already see the notorious nature of this term. We may have a logarithmic term and which will blow up at r is equal to 0. So, we do not want that. So, we want to say that the temperature at the center of the circular tube is finite, which means that the logarithm term should be dropped. So, these are the assumptions subject to which the solution has to be sought for this particular equation. So, as it appears, this equation looks quite painful to solve, but we will do non-dimensionalization so that it can be solved very easily. So, the way we do non-dimensionalization is as follows. We basically want to avoid these constants from appearing. So, we do not want these things to keep sticking around. Okay. So, we want to then go about in this following manner. Look at the units of Q, which is the flux. Then if you take this units, then it comes to the temperature units, and you could then use that as a scaling factor. The reason why we are using Q naught R by K as a scaling factor is because the boundary condition comes out to be very elegant. So, we define the non-dimensional temperature in this manner, so that we remove the T naught from the temperature, so that we are only looking at the relative increase in the temperature, and then scale it with Q naught R by K, so that T star is actually non-dimensional. Now, the scaling for radius R is quite obvious. It should be the radius of the cylindrical tube that we are talking about. So, R star scaling is quite straightforward. Now, the scaling for the Z distance is a little different. We could use R itself as a scaling factor, but that will not help. The equations turn out to be quite messy. So, what we do here is a scale that is actually interesting. So, look at the units of alpha by r square. Okay. So, alpha by r square is basically having the units like 1 by tau, okay, where tau is the diffusion scale, diffusion time for a distance r, which means what you have written here is um tau into um. So, which means that this is the distance travelled by the fluid in time tau, which is taken for thermal diffusion over a distance r. So, which means that by the time, so the analysis is shown here. So, by the time the heat actually diffuses over this distance, how far did the fluid move? So, this is then the Z scale, okay, and this is the R. So, that way we actually have a very intuitive kind of a scaling here, and as it turns out that this kind of a scaling is going to give you a lot of simplification in the equation. So, the Z scale is r square by alpha. So, you put in the reverse, and then you could see that Z star is now non-dimensional. So, now we see these three, and then go ahead and use it to simplify the equation. Okay, so, what we do is first we will take the left hand side term only. So, we take the LHS, and we see that what we need is dou T by dou Z. So, dou T by dou Z is nothing but dou T star by dou Z star, and then you could see that T star into Q naught R by K is what should be there. So, Q naught R by K is there, and Z star has R square. So, the R and R square will cancel, and then you will get the multiplicative factor here, okay, and this becomes the factor that comes because we have done the non-dimensionalization. And when we substitute, will get cancelled, and therefore, the LHS will come out to be in this fashion, where for example, Q naught alpha by K into R is only present on the left hand side. So, make note of this. So, this is only the present on the left hand side, and R by R is already readily there. So, that becomes R star itself. So, left hand side is now fully non-dimensional except for this term. On the right hand side term, for example, RHS, Okay, so RHS term is going to be non-dimensionalized using the same expression. So what we do is that first we look at only this term. So dou t by dou r, okay, and that straight away gives q naught by k because r is already gone with the denominator. So dou t star by r star will give you q naught by k. Now you multiply with r, okay, then you get the second one, okay, then you would get r present because r is coming in the front, and then you look at the derivative of that, then we see that again the r has gone because you gone to the derivative, okay. So again you get q naught by k. Now the RHS will have 1 by r in the front, so again r will come in the denominator. So you could see that you are getting the same term which is multiplication on the right hand side also. So you look at here q naught alpha by kr, q naught alpha by kr. So which means that when we substitute these two non-dimensional expressions, the coefficients are getting cancelled. So that is the beauty of the non-dimensionalization which we have done, which means that finally the equation is going to come like this, which is quite elegant because it has no term except what we look at. So what we now say that I want to evaluate t star as a function of r star and z star, and then this is actually quite nice because in this equation there is no other quantity that is sitting around. Now even the boundary conditions need to be then interpreted with respect to the non-dimensional way we have done, so that we will do. So when we say the inlet temperature is T naught, so because we have already seen that temperature scaling is with respect to T naught, so the boundary condition for inlet condition is that T star is 0, and the flux condition on the wall is giving as minus q naught, which you already saw that we have chosen q naught here. So that actually gives you very elegant boundary condition for the wall as dou t star by dou r star at r star is equal to 1 as just 1. So this 1 is what actually makes life very simple. So when you have zeros and ones in the equation, the integrations become very easy, and that's the hindsight with which we have actually introduced q naught into the t star definition. And then when you look at the finite condition, it is the same, we just leave it as such. So we now have the boundary conditions that are available, so we can now pose the problem as follows. So the problem is now purely mathematical problem, it no longer looks like any heat transfer problem. We say that solve this equation subject to the boundary conditions that are given here, okay. So this again we can directly look up any handbook and look at the solutions. We will actually see how we went about the solution here itself. Now look at the equation, we see that when you take this to the other side, the equation looks rather simple. You see that on the left hand side you have got only the z star only on the left hand side, on the right hand side you got r star only. So which means that the temperature T star could be thought of as a function which is a sum of two functions, that is a function of r star and function of z star. So this kind of a approach will immediately hint. So normally when we look at any differential equation where you could actually separate the two variables on both sides of the equal to sign, which means that the sum of two functions of those two variables could actually work out. So we will then use that concept and propose a solution. So the way we normally go about solving these equations is we propose a solution, then we substitute in it and then see how the solution will come out. So we propose a solution which will look like this, that is a sum of two functions. First function is just a linear function of z star. So we have already made the decision. So remember this is linear. We have made the decision because we dropped dou square t by dou z square term, okay. So which means that we already wanted the z variation to be linear, so that is put, and this is unknown, and we want to know what is that function phi, okay. So this means that the temperature variation along the tube due to the heat flux from the surface is going linearly as function of z star, but there is a correction term that is coming because of the phi, which will give you the temperature variation along the r direction. So this is quite natural, and it is also intuitive the way we know how the pipe flow will be affected by heat flux from the surface. So which then we will substitute. So we substitute this solution into the equation, governing equation. So when you substitute, then you would see on the dou t by dou z star will have only c naught, okay, and on the right hand side you have got only phi, okay. So then we have got a simpler solution. Now what we do is that now that this is there, you could then integrate the left hand side with respect to r star, so that you could get this thing off. So when we do that, r star goes to r star square by 2, r star cube goes to r star fourth by 4. So, this we do by integrating once, and on the right hand side when you integrate once only this will remain, and that is what is actually coming here, and this is the integration constant. Okay. So, now you can see that slowly we want to integrate, so that on the right hand side we have only phi, and the left hand side we have got an expression, that way we got the phi figured out. Okay. So, we now see that this expression is available. So, we take r star to the left hand side in the denominator and then integrate once more. So, that is what we do. So, we have got r star square by 2 minus r star fourth by 4 divided by r will give you r star by 2 minus r star cube by 4 plus C1 by r star is equal to dou phi by dou r star. Then we again integrate with respect to r star, then you see that this goes as r star square by 2 into 1 by 2, that is r star square by 4, and this goes as r star fourth by 4 into 1 by 4, that is r star fourth by 16, and then this goes to the logarithmic term, and then this when integrated will become just the phi, and then this is the constant term. So, we can see that now we have got this guy which we wanted to eliminate, and then we say that the boundary condition which we have already decided that we do not want at r star is equal to 0 any problem in the solution. So, we straight away drop C1. Okay. And once we do that, then the solution looks a bit simpler, and the boundary condition that dou t star by dou r star at r star is equal to 1 will make C naught is equal to 4. So, you have got these two in one go available, because when you substitute r star is equal to 1, straight away you can see how that C naught will come. So, this is the only thing unknown. So, keeping this unknown as it is, we will look at the solution now. The solution looks quite simple, except for one constant that is there, and we suspect that constant should be just a number, but we want the number to be proper. Okay. So, we see that there is no boundary condition that we have which we can use to get the value of C2. So, what we do is we introduce a very special boundary condition which basically talks about the enthalpy balance over the entire domain. So, what we want to say is that whatever enthalpy is entering the domain and leaving, the difference should have come only from the surface. Okay, this is quite intuitive, this is what it is actually. So, but we want to then express it in the integral form, so that the C2 is available in the integral form, so that we can evaluate that C2. Okay. So, because most of the boundary conditions happen to be in differential form, and that is not useful because this C2 will then get knocked off. Okay. So, we say that the difference in the enthalpy flowing out minus flowing in, that is Qz by minus Q naught, is because of the heat flow coming from the surface, and that is basically 2 pi r into z, which is the circumference, into Q naught, which will be the flux that is coming in from the circumference. So, now what we do is that this we then write it as a boundary condition and then see what will happen. Okay. So, that boundary condition, if you see Qz is written in this form, Qz is the enthalpy that is flowing out. So, enthalpy is given as rho Cpt into the area element, okay, and into the velocity. Okay. So, that is basically giving you what is the enthalpy that is coming out. The u will tell you what is the rate. Okay. But that is because in the z direction you have got, you will have, because z over t essentially. Okay. And you have got, this is the area element. Okay. So, you have got area and then z, that is the volume, volume into rho is mass, mass into Cp into T, that is enthalpy, and by T means rate of enthalpy that is going out. Okay. So, similarly what is coming in is written, and then the difference of them is basically T minus T naught into this entire expression, and that basically is written in this form, rho Cp T minus T naught into the velocity into the area element integrated over the entire circumferential area is going to give you the total amount of heat that has come in. Okay. And this is basically the boundary condition that we want to use, and luckily for us we have already non-dimensionalized T minus T naught. So, we have those expressions that is coming quite nicely. So, when we then look at how would this expression look like when we non-dimensionalize, then it would simplify in the following manner. So, we take the rho Cp to the other side. So, you put it in the denominator, and then we would see that the boundary condition we have written comes out to be a very simple one, which is looking like this. Okay. Now, this what we do is that we put the solution of T star in. So, that is what is put in here. So, solution for T star is available and rest of it is as it is, and then we will let see how we can go about integrating. Now, when we integrate, we see that the C2 is still kept inside, and that is what is giving the value of C2. So, the boundary condition, which is an integral boundary condition, is then very useful. Okay. Now, what we do is that we separately evaluate this and then keep it. So, we can then see that this is 0 to 1 minus r square, that is r star minus r star cube dr star, and that would be like r star square by 2 minus r star fourth by 4 evaluated between 0 and 1, that is nothing but half minus 1 by 4 1 by 4. Now, this 1 by 4 is very useful because it comes in twice. Okay, while we integrate, we can bring it twice. So, there is one that comes because of C2 into this. So, that comes straight away C2 by 4. So, we made the simplification and straight away we write that, and then the second expression is coming for the rest of them, and then that integration is going to give you 7 by 96. Okay. Now, this is something evaluated in a similar way as I have drawn written here. So, it is just integration from 0 to 1. So, it is quite straightforward, only polynomial integration. So, that will give you, so this basically gives you that C2 is minus 7 by 24. Okay. So, once we have got the value of C2 thanks to the boundary condition, then we can substitute in the solution and then give the solution here, okay, in the form of T star. The solution is 4z star plus r star square minus r star fourth by 4 minus 7 by 24, and then when we substitute these things in, then you could actually see how the solution would look like in the dimensional form. Okay, so, in the dimensional form, now we have got the solution. So, which means that T as a function of r comma z is now available. So, technically our problem is solved. We are done with the solution, and for the pipe at any r and z, we can then find out the temperature, okay, subject to the boundary condition that the heat flux on the surface is constant, which is Q naught, that is also given here. Okay, so, now what we do is that we go ahead and use this solution to arrive at the concept of bulk temperature and Nusselt number. So, where are we? So, we have set the problem, and this long derivation is done, and we have got the solution. Now, we only need to get the surface temperature and the bulk temperature concept. So, the surface temperature is nothing but at r tends to capital R. So, there is nothing but substituting that r star is equal to 1. Okay, so, that is quite straightforward. We will do that. So, simply substitute here r star is equal to 1, and you get what is T star. So, surface temperature is then given as 4z star, and then this is 1 minus 1 by 4 minus 7 by 24, that gives you straight away this. Okay. Now, this when you expand using the non-dimensionalization expressions, then that gives you the surface temperature as a full expression here. Okay. Now, the bulk temperature has to be introduced. So, the bulk temperature, I want you to think about how you get a warm water shower. Normally, you have got the hot water coming through one pipe and the cold water coming through another pipe, and then you have a knob which allows you to mix the flow rate between the two, and then you have got the warm water here. Okay. So, what are you doing? Basically, what you are doing is the heat that is coming from the hot water and the cold water is getting mixed by a ratio, and then you are getting the warm water. The ratio depends upon the flow rate. So, as you can already feel that if the flow rate was very low for hot water, then you would not mix much of cold water, you will lower the fraction so that you can get the warm water at the same temperature. So, this is some common daily life experience that we are actually using what is called flow average temperature. So, the averaging is done with respect to the flow rate, okay, and that is exactly what is done with the bulk temperature also. So, bulk temperature is defined as flow average temperature T into U divided by U, okay, and in case of a constant plug flow, you just simply multiply the velocity and that should do. But in our case, for example, the velocity is a function of the r, and therefore, you can actually then substitute and then integrate over the entire cross sectional area. So, this is the integration over the entire cross sectional area, and then you can get the bulk temperature evaluated. Now, the bulk temperature actually means that whenever you have the temperature that is varying as a function of r and z, we do not want to put thermocouples and measure the temperature. So, what we do is that at any point at any z, if you were to take that liquid out into a container and then let it mix and then ask what is the temperature of that mixture. and that would be the bulk temperature basically. Okay. So, this concept is very useful to know what would be the effective temperature that is coming out, and the way we evaluate is written here. Now, we are actually dropping the theta integration on the denominator and numerator because there is no theta variation. So, you would get 2 pi in the numerator as well as the denominator if you drop it, and we will simplify the bulk temperature definition with only the R variation here. So, you have got T and then velocity RdR, velocity RdR. Okay, that is the averaging that is done. Now, velocity is already available as an expression, so we can substitute and get this. So, the special boundary condition can be used to evaluate this. What is this? So, when you substitute the expression for T and U, so it will be quite formidable. So, instead of getting lost with respect to that particular algebra, what we do is that a couple of slides back we have used the special boundary condition. So, we will recollect that. So, we have got this done, right. So, use this. So, we write this expression, we bring it onto this slide, okay, and here we write it, and we see that the expression is written, and what we wanted is only with respect to the temperature. So, take the rest of it onto the right hand side. So, which means that we can actually write integral T U R d R is nothing but then written in this form. Okay. So, to the right hand side. Now, once you take it to the right hand side, then it is a constant here. So, you can then go ahead and evaluate. So, we are actually postponing the evaluation of the bulk temperature, we are just using the expression as it is and then reusing the analysis that we have done earlier. So, now when you take to the right hand side, then you could see that the first term is actually coming with a constant, and this integration can be done, and you have got the expression, and the T naught is available in the second term, and then you could then substitute the R by capital R to be R star and simplify your mathematics, so that you could see this integral, and again this integral is reused from what we have done earlier. So, we have done it here already. Okay. So, we reuse that result here and say that there is nothing but 1 by 4. Okay. And the denominator is given here. So, when we look at these two terms, then we get Tb as T naught plus some quantity. Okay. Now, this means that this is the additional rise in temperature as you go away in the distance z because of the flux q naught, and naturally how much of rise should come with respect to rho Cp, and then the time scales etc. are then taken into account by R and Um here. Okay. So, this is how the bulk temperature is then derived and given as an expression. So, once you have got Tb and Ts available, then we can see what happens to the difference between them. Okay. So, the difference is then evaluated to define the heat transfer coefficient is as follows. So, Ts expression we have already derived, Tb expression we have already derived. So, let us look at Ts minus Tb, and that comes to be quite simple, and it comes out to be also something that we already recognize. Okay. So, you see that temperature difference and Q naught are there. So, you have got Q and then there is a temperature difference if you go to the denominator. So, this is somewhat like the heat transfer coefficient into D, there is a length scale, and by K. So, this we already see that it is a very useful kind of a non-dimensionalization that we have done, but please note the K is of the fluid thermal conductivity. Okay. So, it is not the Biot number we are talking about, that is why we give a separate name, it is a Nusselt number. Okay. So, what we do is that we define heat transfer coefficient in this manner, that is for the pipe flow we define as Q naught by Ts minus Tb, and if you define that, then you get this non-dimensional number to be very simple expression, that is just a number 48 by 11, and this we want to define as Nusselt number. Okay. So, Nusselt number is defined in this fashion. Okay. And remember that K is that of the fluid. Okay. In the case of Biot number, K is that of the solid. Okay. So, the subscript for the Nusselt number should always be looked at, because sometimes you may see an expression like this, which means that you are most probably talking about this. Okay. And sometimes you may have an averaging, which means that you may have averaged the way the heat transfer coefficient was measured, etc. So, like Reynolds number, you also watch the subscript and superscript for Nusselt number. Okay. Now, why is this concept suddenly being brought in? The reason is that these correlations for heat transfer coefficient are not available as a raw quantity. You would actually encapsulate with respect to the length scale and the thermal conductivity of the fluid, and then it is the Nusselt number correlations that are available. So, if you look up handbooks, then you already have Nusselt numbers available for various situations, and you can use them, look at the definition of Nusselt number, and then get the heat transfer coefficient correlation. So, for a given situation, if you want heat transfer coefficient, so you want a heat transfer coefficient, first get Nusselt number, okay, and then you can go back and evaluate what would be the H, and then use it as a boundary condition. So, it is very important in metallurgical scenario, you have situations where the fluid flow could be quite complex in various geometries, and we do not have to go ahead and solve fluid flow in all those situations. Very often the Nusselt number for those situations is already available as a correlation. So, we can use it and get the heat transfer coefficient, and then our problem will then become just a conduction problem. Okay, and the reason why this Nusselt number derivation is important is because it comes up in a very elegant manner. It says that Nusselt number is just 48/11 for laminar pipe flow along with the uniform surface flux conditions. So, you could see that even when the surface flux is not constant, but you would have a constant surface temperature, then Nusselt number will come to be a constant, but it will not be 48/11, it will be some slightly lower number. Okay, so, you could actually look up those correlations. Now, there is another situation where Nusselt number turns out to be just a constant, just a number, and we will look at it, and that is a very small problem, and to expose the beauty of the Nusselt number correlations, let us go through that. So, this is a situation of a sphere which is, let us say, hot sphere, which is losing heat into fluid. Now, the fluid we say is a quiescent fluid, that is, it is not actually having advection. So, that I would then use it to drop these guys out, okay, by the assumption 2, and we say that this heat loss is taking place at steady state. So, which means that I would like to drop this term, and we want to say that the heat flow is only in the radial direction, which means that then I would like to drop this. Okay, and then we say that the fluid flow is not happening, so there is no heat generation at all. So, therefore, I drop this. So, which means that my problem is reduced to only this term is equal to 0, which means that the alpha and 1 by r square can also be dropped. Okay, so, my equation is quite simple. It is nothing but dou by dou r square dou t by dou r is equal to 0. So, this is the equation that I need to solve to get the temperature as a function of r away from the sphere, and subject to the boundary condition that on the sphere the temperature is T naught, and far away infinite distance away from the sphere the temperature is T infinity. Okay, so, subject to do that in the domain between r and infinity, let us inspect how the solution would look like, and this is already done by us earlier. So, you could see that this can be integrated twice to give you a functional form of 1 by r. So, this is the solution. You can already inspect that when r tends to capital R, then you get T naught, when r tends to infinity you get T infinity. Okay, so, T naught and T infinity. Okay, and this solution then can be used to define the heat transfer coefficient and then inspect what would be the Nusselt number. So, heat transfer coefficient is defined as the conductive heat flux divided by the delta T. Now, the delta T here is quite obvious, it is nothing but the difference between these two. Okay, so, this is the delta T, which is basically T naught minus T infinity. So, we use that in the denominator, and the conductive heat flux away from the sphere is given by minus k dou T by dou r, evaluated r is equal to capital R, and this is the solution that we have for the temperature. So, we substitute that here, and then we will see that it straight away gives you H is equal to k by r, which means 2 k by d, because we want to then look at what is the expression that comes out with the d, because Nusselt number has that. So, we can straight away see that Nusselt number for this problem comes to be very elegant, just 2. So, you could see that there are problems in which Nusselt number comes to be 48/11, sometimes 2, and so on, and very often it will be a function of various quantities as a correlation. Okay. So, these two cases we know what are the situations for which it comes. So, like this, look out for very elegant expressions that can actually help us in getting the heat transfer coefficient. Now, straight away from here we have some conclusions that can be drawn. Now, what does it mean when we say a sphere will have a Nusselt number is equal to 2? It means that the heat transfer coefficient is given by 2 into k of the fluid around divided by d of the sphere, which means if the sphere is in micrometer size, then heat transfer coefficient is going to be very, very large, which means that when you want to solidify liquid metal, without any partitioning, then if you can spray this liquid metal as tiny droplets, then each droplet would have such high heat transfer coefficient that it would freeze at almost a million Kelvin per second, and then you will have partitionless solidification. You get metallic powder that is very homogeneous. So, in the spray forming of metal powder manufacturing, what you are actually using is that Nu is equal to 2 idea to get the H to be as large as you can, and thereby avoiding slow solidification and segregation, etc. So, you can already estimate how would the heat transfer coefficient be for a tiny sphere by just knowing that Nu is equal to 2, and any other change because of the fluid flow will only be in addition. Okay. Now, there are empirical correlations that are then available for Nusselt number, because we now know the functional form how to go about. Some of these correlations are given as a function of the properties. So, the properties, one of them of course is Prandtl number. We call that as a property because this is basically kinematic viscosity, and this is basically thermal diffusivity. So, both are properties. So, basically Prandtl number is nothing but it is a property of the material, and we want to take a ratio of these two because we are actually looking at coupling of the fluid flow and the heat transfer. And liquid metals are low Prandtl number fluids. Okay. So, this is very important for us to remember, and what happens is that in many correlations, when the Prandtl number is very small, we can make many approximations. So, you can say that the thermal field gets set up very early and so on. So, like that we can actually make approximations, and there are some examples that I am just listing here. So, the complete list of correlations that you would find useful will be available in the course website, but for some examples you can see that the Nusselt number will be given as a correlation like this, for example. Okay, it will be given as a function of Reynolds number and Prandtl number, which means that as the velocity changes, and you can substitute and get the Reynolds number, Prandtl number for that particular fluid you are using, and straight away you get the Nusselt number. The moment the Nusselt number is available, you can get the heat transfer coefficient. So, for example, if you say that I have changed the gas that is actually cooling the flat plate from argon to helium, then how much the heat transfer coefficient will change. So, you could see that it comes via this, okay, because of the Prandtl number, because in Prandtl number you have got alpha, and then alpha is going to be different from argon to helium it will be more, and straight away you can then see how the H will be changing. And then if you say that the flow rate of that gas is doubled, what would happen? Then we see that it is a Reynolds number that is changed, then you can see how the heat transfer coefficient is changing like that. And for all these correlations, always remember that there will be a validity range beyond which you should not be using those correlations. For example, for external flow over a freely dropping droplet of liquid, you could say the correlation is given as 2 plus something. We now know where this 2 has come from. It is from the pure conduction solution, and rest of it is because an addition due to flow. Okay, so we can already see we can make meaning out of these expressions already, and here also the Reynolds number and Prandtl number will tell you how the heat transfer coefficient will be modified as processing conditions or the fluid is changed in a situation like, for example, external flow over a freely falling droplet. Now, like this you can actually look up the Nusselt number correlations for many problems, arrive at the values, and then get the heat transfer coefficient and use it in the boundary condition for the thermal problems. So, over these sessions in both fluid flow and in the heat transfer, we have come across a number of non-dimensional quantities. We have come across the Reynolds number when we were looking at the scaling of the Navier-Stokes equation. We came across the Biot number when we wanted to see how we can choose the lumped heat capacitance method to be valid or not. We came across the Fourier number in that process, and we come across the Nusselt number because we then see that it comes out to be a simple number for many problems where the fluid flow is directly affecting the heat transfer. We came across Peclet number when we saw a situation where the flow is along the heat transfer direction, and we could encapsulate the distance with respect to the velocity and the diffusivity. And then we also came across Prandtl number to find out the ratio of the diffusivities of the momentum and the thermal field. So, there are many more numbers that will be very important in this subject. We will come across them as we do some of these tutorial problems, but for now I think this is adequate for us to look at the heat transfer with and without the fluid flow, and look at the course website for notes and practice problems that are numerical in nature.